Hello, welcome to Math for Designer. In lecture 12, we are going to learn counting principles. So we learn how to count. After all this time, we still need to learn how to count. But we know we are not just counting random things. There are some things that it is. There are some ways or techniques that you help you count faster or count with more precision. So there's this box, but actually, this is meant for the next class, which is the probability. Because if you don't study combinatorics or math in advanced level, like the material for today are just based on they are the base for studying probability. Because to know what is the chance, what is the likelihood of some events to happen, then you need to know how to count. Okay, how many ways we can get this event or this thing that we want over the number of things of all the possible things, and we need techniques or formulas or ways we can compute for these two numbers. But for this class, we will start from counting and see if we can count. Or you can use some kind of formulas or some techniques to help us count. So let's start from the concept. Like there's this question I pull out or I stole from Brilliant. Oh, that's typo. Brilliant.com. That's a nice website, and I suggest you check out the exercises there. And they have interesting exercises you can complete. So here, suppose there are. This is kind of like a solution actually. But yeah, let's go back one step and start from a problem. So let's say there are 9 players. I think the statement is something like ping pong or table tennis players. Right, and this 9 need to know, who is the best ping pong player on campus or in this room or whatever. Maybe they play for a tournament. And so the tournament organizers decide to have them all face each other once. So let's say there are 9 players. Number 1, 2, 3, 4, 5, 6, 7, 8, 9. And these 9 players need to face off or play against another. Each other players exactly one. Like for instance, if you take a look at the first player, at player number 1, he or she they need to face every other player once. So there will be a match for player 1 and player 2. There will be another match, not the same time of course, because they can split themselves. Then player 1 to player 3. And then player 1 to player 4, player 1 to player 5, player 1 to player 6, player 1 to player 7, player 1 to player 8, player 1 to player 9. How many matches are there? 1, 2, 3, 4, 5, 6, 8 matches. So at some point during this tournament, we must have 8 matches for player number 1. And then we have to repeat the same thing for in every other player. For player 2, that player needs to face against player 1. But since there was a match already, we account for that match already, then we don't have to count it again. This will be something that we call the overcount. We count something twice or more than once, and that number will not reflect on what the result should be. So that means we're gonna have to ignore that match, or not ignore, but this match has already happened already. So we don't have to repeat that again. Now player number 2, we need to face against player number 3, and then 4, and then 5, and then 6, and then 7, and then 9, and so on. How many matches are there? 1, 2, 3, 4, 5, 6, 7. 7 matches for player 2. And you can see why this is going right, because then we need to get a player T to play with someone. Oh, sorry, with every other player. But 3 doesn't have to play against 1 and 2, because it has been arranged already. So we need 3 to play against 4, 5, 6, 7, 8, and 9. So that's 6 matches. And so on and so forth. Oh yeah, I forgot to state the question first. Now the question is, how many matches are there? How many matches in the total for this whole tournament? Yeah, question mark. So this is a question about counting. And this is a statement. We try to arrange something, and then we count how many ways or how many pairs we can make. So if you count using this method, like this will be called a straightforward technique, straightforward way to count. Just count them all, and you can kind of guess a trend, right? Player 1 needs 8 matches, player 2 needs 7 matches, player 3 needs 6 matches, player 4 would need what? 5, and then player 5 would need 4, player 6 would need 3, player 7 would need 2, player 8 would need 1, player 9 would need 0. And it's 0 because that player have already matched against every other player. So we don't need to arrange anything else for that player. And so, like based on this naive counting method, then we can just sum all these numbers, which you may or may not have the formula for that. Right, suppose you know, okay, if you sum all the numbers from 1 to n, in this case n is 8, then the result is n times n plus 1 divided by 2. So that's what? 8 times 9 over 2. So that's 72 over 2, which is 36. So the answer here is 36. You would have to arrange 36 matches for them all to face against each other exactly once. So that's one way to count. And the reason I suggest this way first, because you can see that first it is kind of inefficient. I mean it works. If you have no clue, or if you have no other idea, this works. But it is inefficient. In a sense that you have to like ask. It's like you go ask every single players, okay, how many matches have you had already, and so on and so forth. And so that would take lots of time in practice. And also, even if like you know how to write it, then you have to make this kind of like note and draw all these lines and see the pattern. Because actually we see this pattern, like it's 8, 7, and 6. So we get it's 5, 4, 3, 2, 1, 0, all the way down. One step each time we move on to the next player. But we haven't proved that, have we? We haven't proved that yet. That the player number 4 need 5 matches besides the one they have already been arranged. Player number 5 needs 4 matches. Player number 6 needs 3 matches. And we kind of haven't proved that. And so there are sometimes you still have to prove things to make sure that you have caught everything already. And also sometimes whenever you try to count things carefully, there's some error during the counting process. For instance, as I mentioned, some of you may say, oh, player number 2 needs to play against every other player, so they need 8 matches. But in fact, we forgot to mention that, if one plays against 2, then that means 2 also plays against 1 already. So you don't have to arrange 2 matches for those 2 players. There are some errors, right? You might overcount. You might miss some cases. Like for instance, if you write it all, like it is correct. Like if you add h all the way to 1, that's correct. But you kind of like didn't mention about number 9. There could be a number here. You might miss that. Or maybe there's some logic hole in your process. And so counting naively or counting in the straightforward way might introduce some errors that we don't need. And also, it is not practical. And not practical in the sense that, okay, there are 9 players, but what if there are 100 players? And then you have to start from writing numbers from 1 to 100 and see the patterns, and then, write a formula for that. It's doable for now, but if the numbers get large, then we don't want to, just do it one by one every time. So that's why we, if possible, we should avoid counting things in this kind of naive ways. And the question is, okay, if we don't want all these things, like what else? Then the question would be like, then what? Is there a better way to count? Is there a formula for that, or is there a technique or notation or something? So we count a lot, so we give them some names. And yeah, of course, there are some of them that we will see by the end of this lecture. But that's the goal of this counting technique, which is where we have a problem then that we can describe using some keywords in combinatorics in this area of counting things, and then get an answer in a simpler form. Like for instance, like this problem about matching people, can actually be transferred into a problem about graph. If you know some kind of graph, like in this case, graph is just a network of dots. There are dots in the formal way we call them vertex or vertices, and then these lines are edges. It's a collection of vertex and edge. And we have a study of graph where, if you have this kind of graph, which is called a complete graph, it's complete in the sense that every vertex is linked by an edge. There's exactly one edge for every vertex. So this graph has 9 vertices and is complete. And so we can immediately conclude that the number of edges, or in this case, the number of matches, we need to make is C9 9 choose 2, which is 9 times x divided by 2, or 36. Something like that. So once we know some kind of techniques, we can count without counting. We can count by, okay, we translate this kind of problem into something else that we are familiar with, or we have a formula for that already, and then just apply that formula for this problem. So yeah, that's how you count without counting. If you recognize, if you read a statement or the problem, and you see, actually this is that kind of problem, because of these requirements in the sentences, then we can conclude that this is this kind of problem, and thus we can use the formula that you may have learned before already. So that's the motivation of what we do here. And there's a link to this good website called Brilliant. If you have watched enough mathematical content on YouTube, you could see that, this website is everywhere. So yeah, maybe just give you a glimpse on this website. Sign up. Yeah, there's an article for that, which is what we cover in this class: rule of product and rule of sum. Rabbit. And the nice thing about that is there are exercises you can complete. 3, 4. I don't know. Okay. You kind of need to sign up at least. But yeah, there are some examples, exercises, formulas. So what we learned in this class is based on that, but not all of these things. And then there are some nice topics that I wish we have time to cover all of them, but again, this is just an introduction to math class to give you some ideas of what kind of topics there are and where, if you want to study further, where you would go. Not to give you the full classes. So yeah, go ahead and to the website and learn yourself. But for this class, well, what do you have in class? That's all we need. So that's the introduction for coding without coding. Oh, and last but not least, we have some keywords. And whenever you encounter these keywords in the statements or in the questions, you should assume that we are dealing with combinatorics or dealing with counting techniques. So for instance, if you see the word how many ways, this is kind of a vague, ambiguous words. How many ways to do something? And then you could almost always assume it is about combinatorics or counting techniques. If you are asked to choose or select or pick or form a group, like from or maybe from many objects. For instance, if you are asked to choose 3 children from a group of 10 children, you are asked to select a flavor of an ice cream. If you are asked to pick a card from a deck, then almost always expect this to be a question about combinatorics. Right? Or sometimes you are asked to arrange order place. I mentioned an example above where suppose that there are cards with numbers, and then you shuffle them all and then you arrange them in a new way. You can ask, okay, how many ways can you arrange these 4 cards? Like in total, you can have how many ways you can arrange 4 cards where, card 1 and 4 are adjacent. You can impose or you can add some restrictions on these arrangements. And lots of things. Oh, I just say how many ways though. Yeah, indeed, this is about combinatorics. Yeah, so there's another keyword that you might recognize and can identify this problem. And also there's some interesting concept about distinct versus repetition. Because for instance, if I ask you to pick 3 people or 5 people, then you would expect them to be all different. You could label them A, B, C, D, E, maybe. And if you pick D, it's not different from picking E. In this case, we would expect these elements or these people to be distinct. But sometimes, or actually most of the time, like the problem or the complexity comes from having some repetition. For instance, if you want to arrange the words mammoth and rearrange or anagram them all, and you ask how many ways you can accomplish that. And then the problem is you think that there are 3 M's. So if I say, okay, let's move the second M to the first place, move the first M to the third place, and keep everything else in the same place, you can say, oh, that's the same word, isn't it? It's still mammoth. Like even if you switch different M's, you would get the same word. Okay, so that means you haven't switched at all if you treat them as 2 different M's. Like they are the same M's. And so extra cares need to be applied when you deal with some repetition. Like some elements where they are identical to each other that you cannot distinguish. Maybe sometimes there's a bag. This bag has 4 green balls, 2 pink balls, 1 orange ball. And then you've picked 3 balls, for instance. Now you could pick all 3 greens. But these are the same green balls. And that means it doesn't matter which one you pick first or second or last. So you should pick them all. Or these all are the same. Oh, if you pick a pink and then a green, right, when you see them in your hand, you don't see which pink it is, right? You can't tell whether this pink comes from the pink at the bottom or pink at the top. And so this will make things a lot more complicated. But sometimes, like for some basic formulas, it's going to be just slightly more complicated. And so that's the keywords and the idea of how to count without counting, and what kind of problems or statements or ideas we might encounter.